Great. Hi, everyone. Welcome to today's Gifted World Masterclass. I'm Siddharth. I'm one of the community managers of Gifted World. We are an online community founded by some of the leaders in gifted and talented education from around the world. Our goal is to provide a space, a community for students, parents, teachers to really get to know each other and find ways to keep yourselves challenged, right? There are so many ways in which the school system is limiting, and we'd like to give you community resources and events that keeps you challenged, keeps you engaged, and gives you everything that you need to be able to grow in a healthy manner. Okay, so today's masterclass is by Professor Utpal Chattopadhyay. So Utpal is a senior mentor and course designer at GenWise. His passion in life is to firmly establish science as a wonderful culture in developing young minds. So he is running a class in the GenWise in the Gifted Summer Camp that's happening in May and also potentially in July. And today he's going to be talking to us about the hidden mathematics behind some simple puzzles. Okay, so thank you all for joining today, and I will hand it over to Utpal.
Okay, so I was just sending a message saying that please turn on the video if you can. Okay.
Yes, everyone, please do turn on the video if you can.
All right. So, okay. Trying to share, I guess. Oh, it's shaking quite a bit. Is it shaking for you also, my picture?
Now it's not shaking. It was shaking a little earlier, Utpal.
Oh, maybe I'll switch off the fan, but it's 41 degrees in Kolkata.
No, you can keep the fan on. I think it's comfortable to see you. Don't worry.
All right. So, can you see the screen now?
Yes.
Thank you. So, I have a bad throat infection, so chest infection. So I may not be able to speak more loudly than this, but I hope this will do. Okay, so the topic is a very vast and broad one, right? And so what I intend to do is to only take you through two puzzles and just describe or hopefully take you through the exploration of the mathematical structure of these puzzles, mathematical underpinning. And even if you have seen these puzzles, I'm hoping that you will gain some insights into it. Okay, so let's proceed with that. Some basic. Let me see if I can put a new slide show that will be better. Is this better?
Yes, we can see it clearly.
Yeah. So okay. Yeah, so in this time span, we can discuss at one or two or at most three puzzles. The third puzzle, if I get a chance to that, is the one that was advertised in this masterclass. Hopefully, you guys have been thinking about it. And one thing is that whenever I talk to students, I never solve everything to the completely. I leave things so that you can complete it, right? And so this will be no different. Like I said, you may have seen these puzzles and already know the answers to them. Even then, I think it will be important. The discussion may be interesting. So please be patient. And no searching internet during the session. Okay. So one more thing that before we discuss these puzzles, we'll do a simple math problem, which is pure math. I'm actually very allergic to this question that what is the real life connect of this math. For me, math I don't need personally, I don't need a real life connect. So I'll start off with a pure math problem with using numbers only. Okay, again, these problems will look familiar but stay on. And if allowed, you can send me direct messages if I have asked a question, and if I have a chance to look at the messages, I'll see. Post this session, if you have any questions, feel free to write to me at this and mention the context. Okay, so we'll start with the puzzle. Yeah. So here's the first problem, right? So you'll have like 30 seconds. So you're giving two integers 34 and 39. You are being invited to find two more integers m and n, so that if you multiply 34 with m and multiply 39 with n, will end up with 10. So I don't think we need more than 30 seconds. So Siddharth, just keep some timing on these things, please. Yeah.
Sure.
I'll also put a stopwatch here.
Yeah, I'm just.
I think 30 seconds is up, so I'll just say the solution. So that's pretty simple, right? Do you agree? Do you agree with the solution? Anybody disagrees, then you can speak up. Unmute and speak up. I hope not. Okay. So the reason I'm asking all these questions is I make lots of mistakes when I teach, and I don't mind it, because the idea is that if a student catches a mistake, that's even better, and I'll correct. Okay. So the only thing is that, so I gave you 34. I made a mistake. Huh? I made a mistake. Oops. I gave you the wrong problem. What I wanted to give you is find me two integers m and n that you multiply with 34. 34m plus 39n is 101, not 10. I missed out the last one bit. It was written in ink, and drop of water fell and erased that. So now I'll give you a minute. I'll give you a minute, and then you see if you can find this. And what I'll do, I'll go off to this mode. Yeah. So how can I see people, all of them? Okay. Only half a minute is left. Okay. Sachin had answered the previous questions. About 20 seconds. I mean, don't feel pressured. Huh? Nothing will go wrong in the world if you can't find a solution in this time. Okay. A minute. I'll give you another 15 seconds, 20 seconds. Okay, you can stop now. I don't know how to see how many of you can those of you who got some answer, whatever the right or wrong, just use the raise your hand and let's see.
Yeah, Utpal, even if you can't see anyone, I can always report to you how many people have raised their hand or something like that.
Okay, yeah. So anyway, so this was certainly more challenging than 10, right? In previous problem. Yeah. Right? I'm assuming. So now.
So far, no raised hands.
Okay. So it was already a little difficult. Okay, anyway. But actually, sorry, Siddharth?
No, would you like? Oh, it's okay.
No,
I won't give the
solution. I won't give the solution. I am hoping that by the time we end this, they can solve all these problems.
Oh, wow.
Yeah.
Sir, I just joined right now. I didn't understand what happened.
Okay, Siddharth, please take care of that.
Jagat, I'll message you separately. Let Professor Utpal continue with the
class. Yeah. So in general, I will not be able to backtrack and explain, because the time is short. Okay. So if somehow, whatever reason you drop out or you join late, I'm sorry, I won't be able to help. But anyway, the reason I'm saying all these things, that if you have done that 101, which probably happened, then I would like you to solve this problem. Find me two integers m and n. Oh, on the right hand side is nothing magical about it. It's just that I just typed out randomly. By the way, I'm not saying the solution exists, and therefore if you can't find a solution, then you have to tell me whether you can show that there is no solution. Yeah, there are two parts to it. If there is a solution, show it to me. If there is no solution, prove that to me. Right? Okay. So I'm assuming then a problem of this nature has not been known to you, right? I'm assuming. That's good. So you learned something today. See these problems are arithmetical in nature, right? In fact, this goes under the um, under the branch of mathematics, modern mathematics called what is it called? Algebraic arithmetic or something? I don't know. Analytical arithmetic. Doesn't matter. But as you can see, the questions I'm asking are very simple. They require only multiplication, addition of integers, right? I'm not even asking anything that has to do with decimal points, right? So
Yes.
yes. So now the thing is, the next two puzzles that we'll discuss, we'll move to the puzzles now. This is very dry. So next puzzle you must have all seen. Yeah. So take a deep breath and let's quickly discuss the first puzzle, right? Okay. So let me go to the slideshow again. So now the first puzzle. Okay, sorry. Yeah. So raise your hand if you are aware of this problem, you have seen it, you know the solution, you do not know the solution, but you vaguely recall somebody discussed it, whichever way. So that's just like a yeah. So raise your hand if you have raise your hand if you have seen this puzzle. If you yeah. Okay. Advik has raised his hand. That's good, Advik. Do you remember the solution, Advik? Also, just speak out and say. Two participants raised hand. That's good.
No, sir, I forgot the solution to this problem.
Don't worry. So one thing I want to tell you. By the way, I don't know why Genoise has described as a professor or whatever. It sounds nice, but I just somebody who likes mathematics a lot. And I forget a lot of things. I don't. Well, okay, I forget a lot of things, but fortunately, I can rederive a lot of things. Right? I can work from scratch. Okay. So this is a very, very common problem. If you have not seen it, is the problem clear? Anybody wants an explanation what the problem is? I hope not, right? So, would you like to try? Give it a try for 1 minute or 1.5 minutes. I'll switch on the. I'll give you 90 seconds to try it out. Just think how will you proceed. If you have any question about the problem itself, just ask me. Okay. So at home you can try it out with with a beaker. And of course, this means that you cannot guess. You cannot say, "Oh, I'll just pour half the." You can't say that I'll pour half that big beaker and that's it, because you can't estimate. Sonakshi has sent me a message. I didn't understand, so please explain the message, Sonakshi. I'll read it and understand. Excuse me. Okay, in 10 minutes, I will just give the solution. So it's okay. Oh, Sonakshi cannot unmute. Okay, that's because I think the
Oh,
That's okay. No problem.
Yeah. Sorry. Just to enable the class to move faster, if you raise your hand, I can ask you to enable you to unmute. Otherwise, sometimes something will go on, they'll unmute, they won't notice, there'll be
Right.
conversation. So when Utpal is open to it, so just please raise your hand if you have a question.
Yes, that's the best thing. Thank you. So I'll do the solution now. Okay. First of all, understand the solution. So let me again go to the yeah. So this is the solution. Now, if I were you and I was reading this, I'll be like going crazy. It says pour 5 liters from the 8 liter to 5 liter, pour 3 liters from the 5 liter to 3 liter. What is wrong with this, guy? Apart from making my head spin, what is wrong with this way of saying?
Utpal, also Ishan has sent the answer as a in 5 steps though.
Okay.
Huh.
Okay, so voice is still soft and unclear. How is it now, right now? I hope it's okay, better. I'll speak closer. Is it better? I hope.
I'm able to hear you. My request to anyone who's having difficulty hearing, maybe try and get earphones. That
Right.
might help.
Okay. Okay. All right. So I'm speaking better. Okay, fine. Okay. So I hope you had some little bit of time to understand the solution. Don't worry too much. It's basically giving you a sequence of pouring one liquid from another, right? So that you get to 4 and 4. How many steps? Yeah, so somebody has sent me a solution. Okay. Ishan has sent me a solution. Ishan, did you do it here, right here, or did you knew about this before, from before?
Let me just ask Ishan to unmute. Ishan, if you could raise your hand, then we'll be able to.
Yeah. So Ishan, tell me.
Sir, knew it before.
You knew it before. That's okay. Fine. But you knew it well enough that you could at least reproduce the answer. So should I go ahead? I go ahead. Okay. Okay. So the solution is my comment I have here is that the solution is right, but what is wrong with it? The solution is right. If you follow these procedures, you'll get 4 and 4. But you know, there is such a thing as even in art, literature, or anywhere actually, it doesn't smell right. It doesn't smell right, meaning it's ugly, first of all. The way it is stated, it is ugly. The original problem was very beautiful, right? Very simply stated, but it has an elegance to it. So no, mathematics is all about elegance, by the way. I mean, there are ugly parts of mathematics where you do a lot of calculation, but at the end of the calculation, you come up to a stage of elegance. Yeah. So why do you think it's wrong? What is wrong with it? Anybody has a comment? Raise your hands and unmute and say what is wrong with it. What do you find uncomfortable about? So raise your hand and he will unmute you and you can ask me questions.
Go ahead, Prithviraj.
It is too complicated, so some people might not be able to follow it. That's what I think is wrong about it.
Okay. All right.
Isha?
Too many words. Yeah.
What I feel is wrong with it is that it said pour 3 liters from the 5 liter bowl to the 3 liter bowl, then pour these 3 liters back to the 8 liter bowl. Why would we have to do that?
I don't know. Okay. When I say I don't know, I mean that maybe the wording's bad, but it is not ambiguous. I'll do a better description soon. So, yeah, 2 more people, please. Who has raised your hand?
No, it's still Isha.
Okay.
No, Isha and Prithviraj have both spoken. Yeah.
Okay. So I'll tell you what I find very wrong with it. Okay. Suppose you completely understood this solution. Suppose you understood this solution completely. So that you can actually tell somebody with your eyes closed. Somebody wakes you up at 2 in the morning and says, solve this problem, or I'll take your mother and father to a prison. And you understood it so well that you can reproduce. Not from rote memory, yeah? but also from understanding. Even then, something is wrong. Okay, so I'll tell you what I find a couple of things that are wrong with it. So it gives no clue. For example, somebody raised a hand.
No, go ahead, Utpal.
Okay. So it gives I mean, by the way, this is a partial list. Huh? I'm not giving complete answers. So these are my personal answers. You can have your own answers. So it gives no clue as to, is this the only solution or are there other solutions available? Okay. So is there are there other solutions and how to find these? That's one question. And okay, it asks for 4 liters, but suppose somebody asks you 2 liters, how will you do it? If somebody asks you 3 liters, that's easy enough, right? If somebody asks you 3 liters or 5 liters, you just pour into the 3 or the 5, right? So that's why in this 1, 2, 6, 7, 3, 4, 5 are missing, because 3 and 5 are a piece of cake, no sweat. 4 we just solve. I mean, we give a solution, but need to think. But what about how do you find for one? Suppose somebody says, I want to drink water, but I don't want to,
Excuse me. Can I
Yeah.
tell how do we find the 2? Can I please tell that? How do you find of the 2?
Yeah, so I'm not, so all these questions you will answer yourselves after the class. So listen, but this is a question that must come to you. Okay. Right? If you are consumed with the specific problem, and if such questions are not coming to you, that means you are looking only at the very narrow view of a problem and not the mathematics it underlies. Okay, that's the point I'm trying to make. All right. So now, suppose instead of 853, I've given you 98 liters jar, 35 liters jug, and 13 liters jug. And I'm asking you that you get me 49 liters out of it. Yeah, Elisa? Somebody raised a hand? Okay.
No one raised hand.
Having done a 853 problem, does it give me any hint as to how to do it for 98, 35, and 13? I could easily have told you, right? Remember this picture here, instead of 853, I will have 98 or whatever I wrote down there, 35, 30. Right? Apart from all this is a terrible, terrible way to state the solution. Okay. For example, the way it is stated is not clear. Is there an algorithm or is it all guesswork, hodgepodge? If there is an algorithm, what is it? And also, how will you put it to a computer? Ideally, if I give you 98, 35, 13, rather than doing it by hand, you will just feed it in a program and get the answer. Right? So this is a partial list of things that are wrong. And we'll see how to find a solution in such a way that you will answer these questions. Right? Okay. Somebody has sent me a message.
Don't worry, Utpal. Someone's asked for the question. I'll just type it out in the chat. You can go ahead.
Okay. Okay. People have forgotten. All right. But I'll just, yeah. So original problem was this one. The person who has asked, just read it and make a note of it. That's the reason I have asked you to put a pencil and paper. And in fact, I have asked you to do something I have never done in my life, which is taking notes. But nonetheless, so this was the original problem. You have 3 what do you call jars with 8 liter capacity, 5 liter capacity, 3 liter capacity. 8 liter is filled. You have to pour among each other so that you get a 4 liter. And I'm saying an extension of the problem would be that can you do it for 98 liter jar, 35 liter jar, and 13 liter jar to get 49. And why just 49? Why not 5 liters from there? Right? Okay, so move on. Okay. Move on. So the question is there a better way to describe the solution? Let's first understand this. Maybe we need pictures. Yeah. In fact, if you use pictures, it will immediately become slightly better. Can you see the whole picture there, by the way? Is the screen fitting?
Yes, we can see the whole picture.
So Siddharth Bharat asking the question. No, you have repeated the question. Oh, fine.
Yeah, I just repeated it.
Thanks. So everything that is written down in words, pour this, pour that, go take a nap, have a slice of mango, walk out in the hot Kolkata summer days and come back exhausted. All that is irrelevant details are thrown away. And look at the beautiful diagrams, right? Look at the beautiful pictures. Would you agree that it's a better description and solution? And is it clear what is happening at every step? So, for example, look at the top row and the third from the left, right? The 3 to 3. What's happening? What are you doing there? Go to 6 to 0. We poured from the third onto the 8-liter jar, correct? Yes. So I'll proceed assuming that I don't need further explanation of what these diagrams mean, what these pictures mean. And poured these 3 liters back to the 8-liter bowl. Yeah, somebody has a question on that. I don't think that question should be relevant anymore. I'll proceed. Okay. So now the next thing I want to say. So this is a solution, right? Now think deeper. Do you really need even a picture? Why do you need a picture? Why not just like this? This is not a picture. This is a table. In recent years, management folks who have always felt a little bad that they don't know mathematics, they've started calling a table a matrix. But just call it a table. So is it clear that what this picture had and this table has, they're the same content? Do you understand? Don't have to check every detail. Right? So 800 goes to 350. Here also 853 goes to 350. Sorry. I'm sorry, I should have written 800 there. On the left, I should have written 800. Just let me correct it in a moment. Yeah. So that is the on the jar I have written the capacity. So okay, so let me just correct it. Otherwise it will be confusing. So I'll just write 800. Yeah. Oh. Yeah. Okay. Now is it clear? This 800 goes to 350, goes to 323, goes to 620, and that's exactly what this says. Yeah. You can check it. You can have the slides later on, check. But then I asked the following question. Okay, what are you really doing, right? Why do you need to write down these steps numbers? Step 1, step 2, step 3. Do you really need them? Is it not always already in the table? So all you need to do is, now I'll introduce important word here. All we need to know are the state of the bowls in terms of what they contain and the allowed transition, right? That's all you need. So for example, a simple line like this will do, right? The content of the entire verbose 7-step process is contained in this. Do you agree? Anybody disagrees? I hope people are not lost. Okay. So now I want to go back to why I was very unhappy with the original solution. Okay. Remember, I wrote this down that this is the terrible, the solution is right, but what's wrong with it? And I wrote down these things. Okay. That gives us no clue as to these questions. That, is there an algorithm? Can you do it for other jars? So now you see what's going to happen. I'll claim, and you'll see that the way we have described it in terms of states and transitions, this is called a state and a transition. Right? 800 is a state. What's that state? 800 is a state where jar A has 8 liters, the other two have 0. Excuse me. And so on. So now here is the master lesson 1, which even if it's not clear to you now, see the reason I'm saying this master lesson, because I'm kind of tickled by this, the fact that I'm doing a master class. So I thought I'll give a master lesson. So master lesson 1 of N, okay, is you introduce the right notation to describe a problem. And the right notation helps you to think. And the right language clarifies the situation like sunlight removes mist. Okay. In fact, this is one of the most important notion of mathematics. You know, people get upset with definitions, they look dry. And actually the dry definitions come after a lot of thinking. You know, after a lot of discussion, I told you about the states and the transitions. If I immediately, first slide, I give you these like states and transitions without taking to the confusion, you may not appreciate. So, and the right notation will also allow you to think of ideas not present in the problem. I will give an example immediately. Okay, so first question. In this transition, what patterns do you see? Do you see any pattern? Okay, because you must have been told by all your teachers that mathematics is nothing but patterns. You just understand the pattern and that's it. You know mathematics, which is probably true. Then you have to understand, look at the pattern, right? So do you see any pattern in this transition? You don't have to answer, you don't have to make a note to yourself. But if somebody has an answer to that, you can tell me.
You can unmute yourself and ask.
Okay, so I'll give you one hint of a pattern, right? Add in each bracket, add the numbers and see what they add up to. Yeah, yes, you can tell me. I don't know if you're going to raise hand.
No, there's someone named SS who's raised their hand. Please.
Oh, sorry, who is SS now?
Yeah. No, sir. I just put my initials.
No problem.
Go ahead.
Yeah, so I see that in the second, third, and fourth of the sets, the first two numbers is equal to the 3 plus 3 equals to 6. It's given here, and then on the fourth, fifth, sixth, and seventh sets, I see that 6 equals to 1 plus 1 plus 4.
Okay. All right. Anybody else? Yeah, please speak up.
Virat, would you like to go ahead?
We are losing time.
I have a small question.
Yes.
It's in the last part. It says, are there more paths from 440? Shouldn't it be to 800, not 853?
You are asking
So
me
you mean
whether
353.
you are asking me whether I should have written, are there more paths from 853 to 440? Correct?
No. Shouldn't it be 800 in the bottom?
You are absolutely right.
Yeah.
Yes. Thank you. Who is that?
That was Virat.
Great. Thank you so much.
And then Prithviraj also has his hand up.
One second. Let me correct it. Thank you. Very important. I'm so happy that you said it. Makes it worthwhile for me to say it. Yeah. Who else has a hand up?
Prithviraj, would you like to go next?
Yes. The first two numbers of the second one, 3 and 5 are makeup of the first one. Then in the second one, the first and the last number, 3 plus 0 equals to the first number of the third one, 3. Then the first and the last number, 3 plus 3 equals to 6, which is of the fourth one.
Okay.
And 6 equals to 6.
Okay. All right. No problem. The people are trying to look for something. Okay.
There's one more hand up from Ishan.
Yeah, just give me a second. People may not know the meaning of the word invariant. The English meaning of the invariant is something that does not change, right? Doesn't vary. So in these problems, typically you look for something that doesn't change. How many of you have heard of in physics conservation laws? I mean, you can't answer me. So those of you who have heard about conservation laws in physics, that's an example of an invariant in a physical system. The total energy is conserved, right? That doesn't change. That's an invariant, like that. Yeah. Just before I take up the comment, okay, go ahead and tell me now some comments. Yeah.
Go ahead, Ishan. You had asked a question. You were asking a question.
No, sir just asked that what are the patterns in the transition, right? The
Yes.
pattern what I found was like all the numbers in the transition equal to 8.
Yes. Yes. So that is an invariant actually.
Yes.
And that is an obvious invariant, but nonetheless good to know that, right?
Yes.
Why is it an obvious invariant?
Because it the sum of the numbers doesn't change in each bracket.
Right, but why doesn't it change? In fact, it's always 8. Why?
Because the starting the starting capacity of the water was
Very
8
good.
liters, so
Very good.
it should be all 8.
Right. So this is what Lavoisier discovered, which is strictly not true. I don't know if you know who Lavoisier was. He is one of the greatest chemists of all time. And he discovered in chemical reaction, matter cannot be produced or destroyed. So let's see an example of that. Yeah, some more hands.
Prithviraj, your hand is up again.
Yes. So good. I'm glad. So I'll proceed now. Okay.
Go ahead, Utpal. Yeah.
Right. Okay. So now an important comment I made here, that can you backtrack from 440 to 800? Now, do you see all the other thing that that's why I keep asking you to make observations. Why are these arrows going only in one direction? Can they in principle going back in the other direction? Can you go from 60 to 152? Sorry,
you mean the opposite, from 152 to 602?
Yeah, so 152 to 602, can you go? Obviously, yes.
Yes,
right?
People are saying yes.
Yes. So you see, actually, even though I drew the arrow one way, they are all reversibles in this particular case. So one of the strategy I could have developed, instead of starting from 800, I could have started 400 and look for paths that lead to 800. Do you understand? And this is what I meant by saying a right notation will give you more clues than the original problem had. That was the master lesson 1 of N. Okay, I'll move on. So now I'm just stating here, this is a busy slide, but I have explained everything here. So now we can formulate this problem. Not the only way to formulate the problem, but a good way to formulate this problem is to just mention the states and transitions between these states. A state is a particular filling of the glass jug, right? So, so each state can be represented by a triple of numbers, x, y, z, right? This is where a little bit of algebra is needed. X, y, z can change, and we have seen how it changed in the previous slide. X, y, z are all changing, right? Yeah. Like here, then the first one x was 8, y 0, z 0. The next one x is 3, y 5, z 0, and so on. Correct? So any number x, y, z will give you, it will tell you how much water is there in a jar, right? Okay. We want to reach the state 440. The capacity of the jug can be represented by 853, but 853 is not relevant here because we are not given filled jugs. Okay. Here, our starting point is 800. That's the starting state. And we have to find a pathway. Okay. Okay. Now, remember the 98 liter, 53 liter, and 15 liter, or whatever. You see, this description in terms of transition of states, we can apply to that also. Just keep that in mind. we have given a notation and described it in such a way that we can describe it using triplets even for the other case. So how many not steps, I'm sorry, how many states are there? Not steps, but just give me a second. How many states are there? What's the state now again? Can somebody tell me what the state is? Just lift your hand. What is the state? A state is a triplet of numbers x, y, z. Yeah, somebody wants to answer quickly.
Rehan, would you like to answer?
Loudly.
Rehan put his hand down. Then Virat also had his hand up, but
All right,
then he
okay.
put it down.
So for example, if I say 2, 3, 2, 3, 2, that would mean the 8-liter jar has 2. I can't have 2, 3, 2. Okay, 2, 3, 3. The 8-liter jar has 2. The 5-liter jar has 3, and 3-liter jar has 3. Like that, right? So one important thing is that how many states are there. Okay, so we'll spend some time thinking. Now there are potentially. Can you think how many states are there? Remember, in principle, x, y, z can range from 0 to 8, 0 to 5, 0 to 3, correct? X can be 0, 1, 2, 3, 4, 5, 6, 7, 8. In principle. Suppose we think like that. Then y can also be, yeah, Virat?
Sir, there'll be 120.
Tell me, explain a little more.
8 into 5 into 3.
8 into 5 into 3. That we are almost, you're correct. Except that since 0 is also a number, you make it 9 into 6 into 4. Makes sense? Because empty is also a state, right?
Yes, sir.
So you can have 216 states. 9 times 6 times 4. But actually, we have also already said that we will allow only those states where the numbers add up to 8. So actually, the numbers are much less than that. So then the question becomes that how many ways can you partition 8 into positive integers? What's the partition of integers? Like, let's take the number 5. You can write it as 1 plus 1 plus 1 plus 1 plus 1. That's one. You can write it as 1 plus 4. That's second way. You can write it as 1 plus 1 plus 3. That's third way. You can write it 4 plus 4. That's yet another way. So you can count the number of ways you can write an integer, positive integer, in terms of other positive integers, right? And all of you have know of the name of Ramanujan. And Ramanujan and Hardy has a famous theorem about how to count these numbers. Number of ways you can partition. This is a famous Hardy-Ramanujan partition theorem. We don't have to go for that. But I'm just saying, even in the simple problem, deep mathematical things that even occupied Ramanujan comes up. That how many ways can you partition 8 into positive integers, right? So let's not be lazy and do some roll our sleeves and do some calculation. So for example, 8 can be 7 plus 1 plus 0. Just read it. 7 plus 0 plus 1. 6 plus 2 plus 0. Why am I counting 0? Because the third jar can be empty. Similarly, 6 plus 0 plus 2. Right? So this is all partitioning of 8. You agree, right? Partitioning of 8. Except that here the order is important. In Ramanujan's partition, partition of 5 into 2 plus 3 or 3 plus 2 is counted as one partition. Here it's not. Okay? Here the order is important. Order meaning which jar has which. So okay, this is some examples, right? So now you can see that each of these correspond to a state, right? So for example, 710 is the state 7, 1, 0, not 710, but 7, 1, 0. Anybody else? Somebody has a comment to question? Okay, let me proceed. How is it to have 4 liters in a 3 liter bottle? Very good question. Very good. So that is not allowed. You just discovered another condition to be satisfied. Okay? But good point. Actually, so you have discovered, therefore, you know, not only x plus y plus z has to be has to be 8, but Z cannot be more than 3, correct? That's what you're saying. Fair enough. Let's proceed and then we'll take up the question later on. So now these are the states corresponding to this. Now, let me throw a bomb here and just say, so all these states have written down here. Some of this, there is something wrong with this state. What is wrong with the state? Some of these states are not realizable. If you start with 800, some of these states are not realizable. You will not reach a state starting from 800. Why not? See, this is what I call deep mathematics, even though it's simple to state. So let's go back to the rules. The rule was either you fill it, you start pouring, right? The rule is you start pouring. How does the pouring stop? Can somebody tell me? When you are pouring from one to another, how does the pouring stop? Yeah, go ahead. Go ahead, don't go ahead. Tell me.
Yeah, Sachin, would you like to go ahead?
Sir, as per the question, this will stop when any two containers will have equally 4 liters.
No, that is the end goal. But in the rules, when you start pouring, right? When do you stop pouring?
Or sir, it might be when there is no container empty, this can stop.
Okay.
So we
Somebody
would
else can
stop
tell
all
me.
the containers full. So
Yeah. So who is this? Who is this?
Vivan sir, I'm with Virat. I'm his.
Okay. So you are saying that when the thing into which you are pouring has become full, correct?
Yeah, basically there's a restriction on transactions also. So like you can't just have +1 or +2 on for in each container.
We'll talk about that later, but let's just focus on how does the pouring stop. Somebody give me one good reason that I'm pouring, but the thing I'm pouring into, once again, the thing I'm pouring into has become full, so I can't pour anymore. How else does it stop?
Prithviraj, would you like to answer that? How else can pouring stop?
No, sir.
Okay.
The pouring stops if the thing from which I'm pouring has become empty. So these are the only two ways the pouring can stop. The thing into which I'm pouring has become full, and or from which I'm pouring has become empty. Would you agree? Yeah. That means you have discovered one of the rules I've been asking you to discover. I've been asking for a long time here. From this slide onwards, I've been asking you, what are the rules? What patterns do you see in this transition? Look at this. That throughout this pattern, you have at least one jar which is empty, or if not that, then a jar that is full. Do you see that? There is no situation where all the jars are partially filled. So the rules of the game is such that you cannot have a state like 611. 611 means that, it means exactly that. It means that you stop pouring even though you could continue to pour. You violated the rules, right? Okay? So this is a very important observation. Okay? So which I have written
There
down
was
here.
Ishan has a question
about
that.
Yeah.
Sir, you told that the rules of the game are that it should be completely full or completely empty, right?
Yeah.
But from the transition from what I have seen is that the 8 in the transition here, like yes, 602, that bracket, that the 3-liter ball is partially filled and 6-liter ball is also partially filled. It's not completely up to the brim or completely empty.
Which one? In this diagram, which one are you looking at?
The transition part.
Which
Both
one?
cases 620 and 602, she's saying. He's saying.
But one of them is empty, right? There is at least one empty or one full.
No, none of them is completely full.
Doesn't
Because
matter.
it is partially filled.
So how do I get 620 from there? I got 620 because I poured out of 3, right? Correct?
Yes.
So when I
Yes.
poured out of 3, when did I stop? When I got empty. So what
Yes.
was 3 became empty, which is 0. So therefore, the invariance here is that throughout this, there has to be at least one jar, which is either completely full or completely empty. Cannot be either way. So for example, in 620, that third jar is completely empty. In the 602, it's the second jar that's completely empty. Look through everywhere. 143, the third jar is completely full. Do you see that?
Yes, sir.
So now do you understand that what I say? That at least one jug must be full or empty following the rules of pouring. So 611 is not possible. Okay, so now that we have done all this, let's now look at the picture in its what I call magnificent splendor. So there is a very famous poem by Rabindranath where it says that the sun, you display your true self to me of your magnificent splendor. So here is by the way, your beauty is in the eyes of the beholder. To me, it's beautiful. It may not be beautiful for you, but who knows? Why is this a beautiful? What is the picture? Take 30 seconds to understand what pictures are. Don't try to understand the straight lines. It's enough that you understand what the bubbles are. Do you understand what the bubbles are? Do you see your 800 there? So that's the state. Actually, that was the initial state. Somebody wants to say something?
Wait, so first we express like 8 in different possible like summations or states.
Yeah.
And those are the bubbles. But then we have a condition where it can't exceed like first set or first number can't exceed more than 8, second number can't exceed more than 5, so and third number can't exceed more than 3. So we eliminate all the other states that don't follow this rule.
Right.
And then we check if it's possible from one state to another state, the transition is possible, and then we draw a line. And using that, we can sort of plot this graph that you have here, and then you can figure out multiple solutions if there are any, and so on.
Who is speaking?
Sir Vivan.
Yeah, okay. Yeah. So, I mean, that's roughly the idea. You don't have to do it exactly in that way. You can start with 800, and then you can 710 and 701 is 800 to 503 is no a piece of cake, right? Yeah. 800 to what is it? 503 is a piece of cake. So is let's see, 350. Yeah, right. So first of all, let me tell you, without knowing the transition, you can definitely write down all the possible states. So 800 is allowed. Then 8 is 7 plus 1. Okay, let's write down 7 plus 1 plus 0 because that's allowed. 701 is allowed because 0 is empty, and so on. So you see 611 is not there. A lot of undefined states are not there. Okay. So those rules that I just told you about, you can use those rules. And yeah, these rules, that x plus y plus z has to be 8. X has to be less than 8, equal to 8, y has to be less than or equal to 5, and so on. And at least one of the jugs will be full or empty. In that way, you can write down all the ovals. Forget about it. Then you focus on the transition. Okay. Now, what do you notice about the transition? What about What about the transition between 440 and 800? There is a link there, right? You see that? 800 and 440. There is a link. And that link goes from where to where?
Adra, you have your hand up. Would you like to answer?
The red lines, even with all the solutions there are, the red lines represent the solutions we found. We could find many more.
That's fine. We can discuss it later. First, I want to know if somebody has a comment about the link between 440 and 800. I'll come to the red link and all that later on. First, I'm asking understand the links at all. Why is there is something fishy about the link? Not fishy, something interesting about the link 440 connecting 440 and 800. And I would like to tell you what that is. First of all, is the link...
Go ahead, Virat. Your hand is up.
Yeah.
Oh, Virat's hand is down. Okay.
So there is an arrow there, right? It's very clear.
Okay. Adra or SS, would you like to answer?
I'll try. I think the link between 800 and 400 is like 800, and from 800 you take the 8-liter jug, which is very much full, and from that pour 4 liters into the 5-liter jug. That's all.
So mathematics is one discipline where in a maze of things you have to focus and throw away everything unnecessary detail. I'm just asking a simple question. Look at the
Also, you need to take multiple steps before you can reach that. Like you can't.
Okay, listen carefully and answer the simple question. You are thinking too hard. I'm asking you the bubble 800 and the bubble 440. What does it mean? The bubble 800 means the biggest jar has 8 liters, the other two have 0. The 440 is the 440 is the situation where we have got 4 in the biggest jar. Second one has 5-liter jar has 4 also, and the third jar has 0. And I'm asking a simpler question: that why is there a link between these two bubbles?
Sir, because the smallest jar is empty between both of them.
Yes.
So Utpal, Dia has written the answer in the chat.
Let me see.
Dia, would you like to unmute and say it?
Yeah, please go ahead.
So with one movement, you can easily go from 440 to 800 just by pouring from the 5-liter jug into the 8-liter jug. You can easily transition between both of those states.
So you are saying you can go from 800 from 440 to 800? Is that what you're saying?
Yeah, with only
just
one
by pouring, right?
Yes, just by one movement of pouring.
And could you go from 800 to 440 just like that?
No, because that would violate the rules.
Right. So these links represent single transitions between states. Correct? And that one-way link shows that you can go from 440 to 800, but you cannot go from 800 to 440 in one step. Obviously, you can go. So now, let me proceed. Otherwise, the second problem will never discussion. So what do you observe? What are these arrows you talked about? Then some arrows are bidirectional, right? Okay. By the way, not all bidirectional arrows are painted red, only one. So the transition that you have gone, 800, that transition, they are shown in red. Okay. See, 800 goes to 350, that is reversible. 350 goes to 323, that is reversible. 323 goes to 620, that is reversible. 620 goes to 602, that is reversible. 602 goes to 152, that is reversible. 152 goes to 143, that is reversible. 143 goes to 440, that is reversible. That means all that you have to do is to look for, you can start from 440. Instead of starting from 800, you could have also started from 440 and look for reversible paths. Actually, there is one. I've given the answer there. There is another reversible path starting from 440. And because it is reversible, you can then reverse it back. So I have not drawn that picture with another color. But the point I'm trying to make, and I'm proceeding, this is a master lesson 2 of 2. Let me see that. You read that. You read that. In the meanwhile, I'll read the. There is no, somebody has HP, I don't know who that is, but she asked me a question. There is a link between 400 and 800. There is no 400, right? Is there a 400 there? Because 400 doesn't even add up to 8. It will not be there. Okay.
I think it was just a mistake. They meant to say 440 and put.
So now all that I'm saying is, see, I'm kept focusing on the right language, the right way of representation of this problem. So what we have done, we have essentially transformed the problem from pouring water to a very important area of mathematics called graph theory, which is a study of nodes and links between them. Okay, and finding paths between these nodes following some rules. And there are many, many powerful algorithms already developed. Dijkstra has done a lot of them. And therefore, it's a problem in graph theory. And if you started with 98, and by 98 liters, and pouring it in 45 and 13, you have to do the same thing, except that because you have analyzed it in this way, you can actually put it in a computer. You have an algorithm now. And then actually it helps sometimes to analyze from back. Okay, anybody else? Otherwise, I'll leave this problem now.
I think we can move to the next problem.
So have we learned anything? Did you, when you started this problem, did you anticipate that we have a deep connection with an area called graph theory?
Yes, it's actually very similar to like other problems like traffic optimization also.
Yes,
like,
absolutely.
Plot
Absolutely.
as nodes and then.
Absolutely.
Yeah.
Oh, by the way, and the forbidden transitions, you can also put them as links with infinite weight. It costs you infinite amount of time, amount of money. All right. So I hope you have, this has been, if you are not kind of floored with this, but okay, I hope you are mildly amused. So we'll move on to the next problem. By the way, so I want to answer the question. What about 98, 35, and 13? And here I'll just quote a theorem. By the way, here A, B, C are in the reverse order. So it's like will be 3, 5, 8 as opposed to 5. I've been writing 8, 5, 3, but A, B, C are in the order 3, 5, 8. But basically it says that if you have 3 jars, A, B, C in ascending order, and C equal to A plus B, and A and B are mutually prime, that means there is no common factor, then you can actually find a configuration which will have any quantity between 0 and C. Okay? You should think about it and understand. For that, you don't need graph theory. You need thinking only. But I'll leave it at that point. Okay? So I've answered all the questions. So you can also do this, by the way, on your spare time. Excuse me. Okay, I will not do this problem here. Okay, now on to 2 jugs problem. Okay, so this is a problem that was, I don't know how many of you have seen Die Hard 3. When I was your age, Die Hard 3 is not a movie that your parents will recommend for you to see. But now it doesn't matter what parents recommend or not. You can always go and find a way to see these things. So basically now we have only 3, not 3 jars, only 2 jars, 3 liter and 5 liter. And you have an infinite supply of water and infinite sink of water. And you have to again create 4 liter water. Okay, so that's the problem. So by now we have to look at state transitions pictures. So here is the first solution. Okay, so look at the solution a little bit. I'll go fast a little bit now. So the state transitions are here, not in square brackets, but doesn't matter, right? The same idea of state transition. X, Y represents X amount of water in jar jar 3 and Y amount of water in jar 5. You can again do a state analysis. In this case, however, you will have infinite number of states. Can somebody tell me why? In the previous case, we had finite number of states. Here you will have infinite number of states. Potential. That's because you have an infinite sink and infinite source. But ignore that comment. See if you understand this problem. So 0, 0 goes to 3, 0, right? You have filled up the jar 3. Then you put that 3 into the jar 5 jar, right? I'll give you another 30 seconds and then we'll move on. So this is one solution. Just satisfy yourself, this is a solution. Okay. What about the previous rule that at least one of them has to be either completely full and completely empty? Looks like that should still be valid, right? Because when you fill it to the full. So if you're filling it, you fill it to the full. If you're pouring it, then either you pour it in the sink, that means you're pouring it out completely, or you pour it out onto the another one, and you can stop only if the other one is completely full or you yourself are empty. So rule still over. Okay, you have seen this. So there is another solution by the way. Okay, this is another solution. I am not written the state transition diagram. Actually, there are infinite number of ways you can do it. You can do it as complicatedly as you want.
So there's a problem here, right? If how do we get infinite? Like if you think about infinite states, right? We can't exactly measure what the amount of input that's going in because we have an infinite source. We can have 2.1 liters or 2.2 liters in the first step. So that might lead to like basically infinite states. So how do we eliminate?
That's not what I meant when you have infinite number of states. But how will you have 2.1? Just explain to me. That's a good point. But please think and loudly explain to everybody how you can have 2.1.
So okay, so like in the last cases, it was fixed. Like we could either like because we weren't allowed to keep the water out.
Take this case and tell me how will you get 2.1 within these rules?
Because we don't have an exact measure. If we just keep it and if I keep a jug under the tap for 5 seconds instead of 4 seconds, that would
no, that is not allowed. The rule is clear that when you go to fill, you have to completely fill. You cannot take 4 seconds and 5 seconds. So understand the rules.
Okay, sir.
That's a good question. I'm so happy that you asked a question because that means you have been thinking. And out of 50, there are 5 people who are thinking. That's good enough. Not because I don't care about the other 45, but because these are not simple things, and you guys are still young and may not be able to catch up on it. So does that answer your question?
Yes, sir.
It goes to clarification of the rule that when you fill even to the source, infinite source, you fill completely. When you pour to the infinite sink, you pour it out completely. If you're pouring to the jugs, then you stop only if your originating jug is 0, empty, or the going jar is full. Clear?
Yes, sir.
Thank you so much.
How would there be infinite states like you mentioned here?
No. So the states is that, so suppose you put another bracket there for the source and the sink, right? Instead of 0, xy, you have x, y, z, and t. And you keep z and t for amounts that you have poured out. Or
Okay. Yeah, but we don't have, but our only limiting factors are the jug, so we don't need to keep the sources.
That's correct. In some cases it may be useful, otherwise not. But fair enough. I'm so happy you are asked this question. Okay, let's move on. So this is the 2 scenarios. Okay. In fact, as you can see, the first one took 8 steps, the second one took 6 steps. Now, see the pattern in this. Suppose I tell you in the first case, you see you have filled the 3 liters 3 times and emptied 5 liters 1 time. Do you see that on the left? The left procedure. Have you filling up the 3-liter jar 3 times and emptying the 5-liter jar 1 time and doing hanky-panky in between. By hanky-panky, I mean just pouring one to the other. And lo and behold, 4 is actually equal to 3 times 3 plus 5 times minus 1. So those are the 3 times you have filled it up, and that is the 1 time you have emptied it. Similarly, in the second case, you have how many steps you have, I don't know, but you have filled the big jar, 5-liter jar 2 times, and you have emptied the 3-liter jars 2 times. And lo and 4 equal to minus 2 times 3 plus 2 times 5. And this is no accident. This is no mere accident. By the way, you should also note the number 1 is equal to 2 times 3 plus minus 1 times 5. And that is also no mere accident. So let me ask you an interesting question now. So instead, you can now revert. Suppose I give you any number here, right? Suppose I take a bigger jars or whatever, and I give you this decomposition in terms of 3 and 5. So let's take the other. In general, if the jugs of capacity A and B contain X and Y amount of any time, right? The jugs of A and B, in our case 3 and 5, and they contain X and Y amount of water. Then you can prove by induction that the X and Y must be both divisible by the greatest common divisor of A and B. All of you have learned about G, greatest common divisor. That has been very boring, very annoying. But in number theory, greatest common divisor occupies the role of a jewel. Many theorems. In fact, your ATM transaction security, they're all critically dependent on the concept of greatest common divisor. Anyway, that's another 1.5 hour lecture. But the point I'm trying to make, suppose you had, instead of 5 and 3, you had 24 and 25 jugs, right? And you are doing this process. Now 24 and 25 are relatively prime, right? Any two consecutive numbers don't have any common factor. Then you can prove by induction that in this process of filling and emptying, the configuration should be such that so of course if the greatest common divisor is 1, doesn't make sense. But the greatest, suppose you check 24 and 20, right? What's the greatest common divisor of 24 and 20? 4, right? Yeah. So then you can show that if you took the jars 24 and 20, then the amounts that you can have in these jars must be divisible by 4. With all these, and I'm doing a very unfair thing because this is so new to you, but I'm going to. Okay, so one more thing. So there is a very deep and elementary result from number theory. Okay, you take any two integers, 3 and 5, 24 and 19. Then, and you make these linear combinations, meaning you multiply one of them by another integer, the second one by another integer, and just add them. And you do randomly. Then the theorem says that you can express the greatest common divisor as a linear combination of this. So for example, here, 1 is the greatest common divisor of 5 and 3. And here we have written that as 1 equal to 2 times 3 plus minus 1 times 5. So for example, here your m equal to 2 and n equal to minus 1. Okay. Now this theorem was discovered in 1779, but in reality, Aryabhatta did it in 800, 900 years ago. You should hear a set of lectures by Bala, I think Bala Iyer, the Kutuka method of Aryabhatta. And the genius of Aryabhatta gave a computational algorithm that actually calculated the GCD using this mechanism. Actually, this is mechanism you were taught in class 5 or 6 or 7, I don't know when, but you are never told the deeper understanding of this. But bottom line is that, so now you can see the one fallout. If you can write 1 equal to 3 times 2 plus minus 1 times 5, you can then express any integer as a linear combination of this 3 and 5, right? Look at this, look at this, what I've written here. Look at this statement. In this statement, I have expressed this horrible number 9, 1, 2, 3, 4, 1, 2, 4, 1, 2 as a linear combination of 3 and 5. How come? How? By just multiplying the previous equation by that horrible number. So now, the reason I'm doing all these things is that, but the Bayes' theorem says something more. It says that if you take two integers a and b, and you're trying to find solutions to ax plus by equal to another integer, z, right? Suppose you want to solve 3x plus 5y equal to 797. Then it has a solution, okay? But suppose you are trying to do the same thing with 20 and 24, 20x plus 24y equal to 3, you won't be able to find solutions, okay? That's obvious because these are even numbers, so you shouldn't be able to do it. But bottom line is that this equation ax plus by equal to z has integer solutions only if z is a multiple of the greatest common divisor. So for example, look at that horrible equation, 74 plus 185y equal to have written down 38 some millions or billions or trillions, I don't care. It has no solution. And how do I know that? I know that because 74 and 185, the greatest common divisor, the highest common factor of 74 and 185, I think is, what is it? 37? I hope I have not made a mistake. 37, right? Yeah. So that
Yes.
means everything on the right hand side has to be a multiple of 37. Whatever you do in life, and whatever political parties tell you, whatever religions tell you, 38 billion or trillion can never be divisible by 37. Do you agree? I hope I'm right. With all this, let me do the last bit of problem. So you have two jugs, 7777 liters and 1239 liters, and want to measure 3 liters. Can you do it? Same problem. We have the same two jugs, but you want to measure 14 liters. Can you do it? So everything that we have said so far means you should look for the greatest common divisor or highest common factor of 7777 and 1239. This is something you can do in class 6, class 7. You can do the calculation. And the answer is 7. So 7 is the highest common denominator. Now remember I told you that the greatest common divisor can be written down as a linear combination of those two numbers. So here I wrote it down for you. 7 can be written as 408 times 1239 minus 65 times 7777. This is the linear combination. There is a way of calculating this, by the way, and that is the calculation given by Aryabhatta around 700 common era, much before Bezuit. So that means if since 7 is the common factor, that means just multiply by 2, right? So then you get what? Sorry, you don't have to multiply, but you can also write 14 equal to 47 7777 minus 295 129. That means, what does it mean? The punchline here. Remember this picture. Here 4 equal to 3 times 3 plus 5 times minus 1. That means you have filled 3 5 times, emptied 5 1 time. Here 14 is 47 times 7777 minus 295 times 1239. That means to achieve 14, there is a way of doing it by filling up 7777 47 times and doing it nicely and carefully and algorithmically, emptying the other one 1239 295 times, and you will get 14. If this makes your head like spin, I hope it does make your head spin in a nice way, because you know that if you sit down and study, go through it yourself, it gives you a tremendous power that you have solved a huge amount of problems in one go. By the same token, the first problem is not solvable. Using 777 liter jar and 1239 liter jar, you cannot measure 3 liters because 3 is less than 7. 7 is the GCD. So 3 is not divisible by 7. And therefore, you cannot measure out 3 liters. So master lesson number 3. So this is more not a lesson. This is more like a life's philosophy. So whatever you do, whether you write poetry, whether you go into what are the big new things now? Entrepreneurship. What else? Or you just go become a yogi. But not like Baba Ramdev, because he's being thrashed by the Supreme Court. That yogi in the sense that you don't care and you will live on your own, go into a forest or the Himalayas, and if you are sick, you suffer and withstand. By the way, a mathematician did that. One of the most important mathematicians of last century, Grothendieck. Just give me a second. Radha, I'm giving this quote unquote masterclass. Call you back. Bye bye. So Grothendieck, one of the most important mathematicians, was an architect of algebraic geometry, got a Fields Medal. And then he didn't like the political compromises being made. He didn't like the fact that his funding was coming from the same government supporting war. So he did leave everything in the world and went into a mountains and forest, never to come back. It's a miracle that we know that when he actually died. But nonetheless, do not be afraid of formulas and equations. Think mathematically. Think through numbers, and when needed through diagrams, geometry, graph theory. Ultimately, everything will come down to numbers. Arithmetic is the prince of mathematics, as Gauss had said. And algebra is the language of modern mathematics, whether you do geometry or not. But most importantly, look for the deep results hidden in this. The reason is, you will love the truth because it never deceives. And the mathematical truths that was discovered 2000 years ago, a physics textbook can become obsolete, but not a math textbook. So look for mathematical truths because no political party and no religious discourse can change it. So that's all about the water filling problems. I guess you must be tired. I don't want to go through this one. You can have the slides and I'll just thank you. So I wanted to do 15 minutes question answer session. If there is time, I can still do it. I'm free. It's up to you. Siddharth, over to you. Everybody is like feeling, my God, Utpal has hit me with this 7777 liters of water on the head.
Thank you, Utpal, and thank you, everyone. So please feel free to send your feedback about this session to me in the chat, or you can. I'd love to hear for it so that we can organize more. And yeah, the stage is open. If you have any questions that you want to ask,
we can have five or 10 minutes of quick question answer, right?
Yeah, yeah.
Yeah.
So go ahead, Virat.
So actually, Vivan, actually, sir, about 2 years ago, I came to GenWise when Naveen Kabra sir was teaching the AI thing. I actually lost your email address, Utpal sir. Could you just, can I just take it down?
Siddharth, you can help him, right?
Yeah, I'll send him your email.
Not mine, Naveen's email.
No, he wants Utpal's email. Wait, sorry, whose email do you want?
I wrote it down. Okay, I'll just write it down. Okay. Yeah.
And Utpal, you are comfortable sharing your slides with everyone later, right? So I'll share it in an email afterwards with everyone.
No problem.
Is that fine?
I have no problem.
So could you also share Naveen sir's? I just want to meet him to like message him.
Yeah, I'll share that with you, Virat.
I'm not going to put Naveen's on this slide, but yeah.
Yeah, I'll share that, sir, personally with you, Virat. Vivan, sorry.
Any other question? Any other mathematics question? Okay, so then I'll ask questions. Can somebody share one or two things that was new or that was striking? Very quickly, yeah? Okay, so yeah, somebody has asked an important question. If you don't have any questions, are you supposed to leave? You can leave. I suppose so, right, Siddharth?
Yeah, I'm just going to quickly ask you to how did you find the class? And it's an anonymous poll. So please do answer it if you're able to. That will be very helpful.
Yeah, please do that. Yeah.
I think you should be able to see it, right? No? Okay, wait. I'm new to this polls business. No worry. I will do it next time. My apologies. It didn't seem to have worked.
I'm going to
But-
unshare it.
Yeah. No, please just do send me your feedback in the chat. I will keep track of it. I will figure out how to do it as a fancy poll later.
Okay. Anybody has questions on there are 7 comments and so on and so forth. I'll just stop sharing now. Okay.
Yes.
Thank you very much. You know, the good thing about this is that I had to work a lot. I had to work hard to put together the slides, right? Because even though these topics are known to me, it was not easy to, you know, put together in a way that makes sense. Even now, it may not make sense. So I worked really hard, and everybody who knows me that I always prepare until like an hour until I have to speak the talk. So this is no exception. So yeah. So I hope those of you who got something out of it, thank you. And you know, if mathematics is your calling, go for it. If computer science is your calling, go for it. If writing poetry is your calling, go for it. Thank you.
Thank you so much, Utpal. I'm getting a lot of very high ratings for the session. So nearly everyone has filled the poll. So thank you for giving all the information. And so thank you, everyone. Our next masterclass is on the 18th of April, where Radha Gopalan will be asking the question, where are all the women of science? So it's going to be a very different flavor of session from Utpal's today, but also look forward to seeing all of you there. And do keep engaged on giftedworld.org. Our blog will keep posting up new things, and I'll be sharing the Utpal slides with all of you. The recording of this session will be up on our YouTube channel by next week.
Can you send me a copy
of the recording?
Yeah.
Yes, will do.
If possible. Yeah. Also, please send me save a chat and send it to me. I will see if there is some questions there.
Yes, I will do that. Yeah.
Okay.
Thank you, everyone. I hope
Bye.
you have a good weekend. The next session is 18th April. All the details are there on the Gifted World website. You'll be able to see it, and you'll get an email about it since you've attended today's session.
You must mean May, isn't it? Because 18th April is gone. 18th of May.
18th of May. So sorry about that. 18th of May.
But did you specify the year? You still
18th of May. 18th of May 2024 is the next session with Radha Gopalan.
You still had a way out next year.
So we'll reach out to all of you on email about it as well. So see you there.
Bye.
Okay. Thank you so much, Utpal. Thank you, everyone. Have a lovely day.